go on page 25 when we're done. We're going to talk about polynomial functions and rates of change. So polynomial functions, not new to you, all right? Although you may have never seen this crazy looking thing here, so let's talk about what this says. A polynomial function is any function representation equivalent to the analytical form of this, okay? And so that looks horrific. But polynomial is just like 3x cubed plus 2x squared minus 5x plus 7. That's a polynomial, right? As many terms is what it means. So mathematically, when you have a generic form of something, you have to use like extra variables and whatnot, and most of the time it makes it look way worse than what it really, really is. So we have this a sub n times x to the nth plus a sub n minus 1 times x to the n minus 1. So so this is in standard form, which means our highest exponent would be first. So if this was x to the 7th, this would be 7 minus 1, which is 6, 7 minus 2, which is 5, and so forth. That's why it's written that way. And then this a sub n, that's just numbering the coefficients that go along with them. And then it says where n is a positive integer. So this n that is the exponent and also is the label on the coefficient, n has to be a positive integer. So if you have an x to the 1/2 power term in there, that is not a polynomial. If you have x to the negative 3 power, not a polynomial. It's a graph, we can do stuff with it, but it's not a polynomial because it has to be the exponent has to be a positive integer. Okay, we good with that? And then a sub I is a real number for each I from 1 to n. So what that's saying is all of your coefficients have to be all of your coefficients have to be real numbers. So if you have an imaginary number as a coefficient, it's not a polynomial, right? And then a sub n is non-zero. Your first coefficient can't be 0 because it zeroes out the term and then you don't have a first term anymore. So that's how that works. So your leading term in this case is this first one, not because it's first, but because it has the highest exponent. In standard form, it's first, but things aren't always written in standard form. So this, my leading term would be a sub n times x to the nth. The degree is the highest exponent you have in your list of terms. So in this case, it would be n, because this is my leading term. And then my leading coefficient is the number that goes before my variable, which in this case would be a sub n. Okay? What questions do you have? We good on that? Okay. No. Yes, these n's would be the same, yes. But when you actually have one written out, it's going to look more like this, and you don't even see this n. That makes sense? Most of the time, you're not even going to deal with that n. But yes, because what that tells you is that this is the, let's say, like it was x to the 7th. This would be a sub 7, and then a sub 6, and it just kind of numbers it so you know which one it goes with. Good question. Anything else? Okay. All right, so we're going to find the leading coefficient and the degree of the following polynomial functions and talk about some other things along with it. So on A, my leading term, this is my leading term, not because it's first, but because it has the highest exponent. Because this one that doesn't even have 1 on it, what's the actual exponent even though it's not there? 1, okay? So it's like x to the first. So 4 is bigger than 1, so that makes my leading term. But then my leading coefficient is what? 3, because it's just the number. And what's the degree? 4, okay? So this is a 4th degree polynomial. So tell me, in a 4th degree polynomial, how many possible real zeros do I have? In a quadratic, how many possible real zeros do I have? 2. So in a 4th degree, how many think I have? 4, okay? So I have 4 zeros, but they're not necessarily always, just like with a quadratic. Every quadratic has 2 zeros, but they might be imaginary. So, but we have a possibility of 2 real zeros. So in a 4th degree, whatever the degree is, that's how many possible real zeros you have, the real ones that we can actually deal with. All right, so with that said, we're going to sketch a little function here. You're not going to have to sketch them on your own. I'm just trying to kind of pull all this stuff together. I'm not trying to actually graph this particular function, because I'd have to know some more things, and that's not really necessary here. But I'm going to say if I have a 4th degree, it is possible that I could have 4 real zeros. So I'm going to put little hash marks here. That's where my 4 zeros would go. And the zeros are where we intersect the x-axis, right? So if I was to sketch something in, it might look like this. I go down and then up and then down and then up, something like that, okay? So I've intersected that x-axis 4 times, right? So with that being said, we're going to talk about turning points, and that actually comes a little bit later in the lesson, but I want to talk about it with this, plus we've already talked about the other things, so it's fine. But if I start here with my function, and my function is decreasing till I get to here, right? Then I'm increasing to here, then I'm decreasing to here, then I'm increasing. When I change from increasing to decreasing, that's a turning point because I literally turned around and went the other way, right? So I have a 4th degree. This has 3 turning points, okay? Remember, we have a possibility of 4 zeros. I don't necessarily have 4 zeros, so I wouldn't necessarily have 3 turning points. But if I can have at most 4 zeros, then I can have at most 3 turning points, okay? So I can have up to 3 turning points. Does that make sense to you? The other thing that we're going to talk about a lot, it's going to go along with this, is end behavior. What is happening at the ends of our function? And that means, like, even though I have these arrows that look like they're going straight up, we're still going out to the infinities, right? So this is my end behavior. The other stuff is middle behavior, which we can talk about later. But just by looking at this function right here, I know exactly what's going on with the end behavior. Middle behavior, I'd have to find some other things out about it, but it'd be possible. We're just not going to do that. But here's what we know. If this was a quadratic, right? Let's pretend like this was an x squared. Then would this open up or down? If this was x squared instead of x to the 4th, it would open which way? Up. Why? Because the 3 is positive, and if the 3 is negative, then it would open down, right? So every even number polynomial, all of them, their end behavior models a quadratic. Now, the middle behavior clearly different than a quadratic, right? And not all 4th degrees even look like that, okay? Or even close to that. But because this is an even degreed polynomial, I know that my end behavior is either up, up, or down, down. And whether it's up or down is the same reason as it would be for a quadratic. That's why when I sketched this one, I know at the very least my end behavior is right. The rest is probably a hot mess because I didn't even try to match it up, but I know it has to end up, up. You with me on that? Okay, because that's something that's going to come back around when we talk about some other things. All right, now let's look at B. On B, what is my leading term? Negative 7x cubed. That's my leading term, right? It's not first, but it's the leading term because it has the highest exponent of 3. So the leading coefficient is what? Negative 7. And my degree is 3. Okay? So if I have a 3rd degree polynomial or a cubic function, I can have at most how many real zeros? 3. And it's possible I'd only have 1. So if you think about a parent function of a cubic, the parent function looks like this. And that only has 1 zero, right? And that's because it gets repeated. It's a triple zero is what it is. But it only has 1. But we could have up to 3 once you start doing some transformations and whatnot. So we're going to sketch one of those. Let's sketch this. And we'll put in 1, 2, 3 zeros. We'll pretend like that looks good. Okay? And so I'm going to start up here again. So I go down and then up and then down, something like that. So notice that when I have 3 zeros, I started up, but I ended down. And if I started down, I would have ended up, right? Because if I have an odd number, if I start up, I end down and vice versa, okay? And because if I did 5 and I put 2 more in, then I would have to go up and then back down, and it would still be the same. So the end behavior of an odd degreed polynomial follows the end behavior of a cubic, right? And if you look at this end behavior is down, up, right? This end behavior is up, down, but the reason I did that is because, again, I'm not trying to actually graph this, but this has a negative leading coefficient, which means it would reflect it, and that's what changes it to up, down, okay? And we'll come back to all of that. I'm just mentioning it. I think the more we mention it and see it, when we come back and really have to do all of this stuff and talk in behavior, then it'll make a little bit more sense. But what this does tell me, since I know it's opposite that way, if I have the degree of 3, then this gives me 2 turning points up to 2 turning points. You do not have to draw a graph to figure out your turning points, but all you have to do is know the degree. You take the degree, you subtract 1, you can have up to that many turning points, okay? And then the only thing that I need you to remember about in behavior of these right now is that for an even numbered polynomial, it's like a quadratic, so it's either up, up, or down, down, and then odd is just like a cubic, and odd is opposite, so up, down, or down, up. And which one it is right now doesn't even matter, okay? But that's going to lead us into something else towards the end of today, okay? We all good so far? All right, I'm going to give you a minute. At your tables, I want you to talk and actually talk about C. And then we will talk about it together. Talk to each other. Talk to each other. Ask them, not me. That's why I want you talking. Okay, let's talk about this. I expect probably 2 different answers, right? And remember, it's okay to be wrong, because I understand why you would think about either one of them. Anybody want to be brave enough to give me a number for the leading coefficient? What do you think? 4. Anybody have anything else? Anybody think none? Because I got that earlier today. Okay, you want to defend why it's 4? It's the biggest number because it's the only thing there, right? Which is what. So let me ask you this then: are you super confident in that, or was it kind of a guess because it's the only thing that's there? Is it kind of a guess, or just like the only thing that makes sense? And that's okay. All right. So let me ask you this: if it's a coefficient, co means with, right? So coefficient kind of means it's with a variable. So all of our coefficients are before a variable. We don't have one here, but that doesn't mean that 1 doesn't exist. If I put an x here, now that changes it to 4x. I don't want it to actually be 4x. It needs to stay and have the same value. What exponent can I be on that, or can I put on that so it doesn't change the value? 0, because anything to the 0 power is 1. So if I have 4x to the 0 power, that's really still just 4, yes? So even up here, when I have x squared right here, and then x, and this is a sub 0, we could put x to the 0 power up there, because see how the 2 and the 2, the 1 and the 1, the 0 and the 0, we just don't put that for the same type of reason we don't put the 1 in front of an x, because it's just not necessary, right? But because we can write it that way, and that's technically what's kind of happening, then our leading coefficient is 4, and what's our degree? 0. And what does that graph look like? Horizontal line. So it looks like this, okay? Now, even if we had a linear function, well, this is a linear function, but if I had like 2x plus 3 or something like that, 2x plus 3 would look like that, right? And if that was y equals 2x plus 3, what's the degree here? 1, okay? Do either one of these have turning points? No. So 3 minus 1 is 2. 1 minus 1 is 0, so there's 0 turning points. 0 minus 1 is negative 1, and that just doesn't even make any sense. So whether the degree is 0 or 1, we have no turning points. Okay, we okay with that? Any questions? Okay, So let's get to this fancy word extrema that was on your quiz. Extrema. It's just a plural of extremes. Okay? Your extreme values, which should in general not be new to you, the term we use might be a little different, but the extrema of a graph, they're the minimums and maximums. It's just the minimums and maximums together. Okay? They fall into the category of extrema because they are extreme values. There are two types of extrema. And both of those types have two names, and we have to know both names for each one because you will see it both ways, and you may even see it both ways on the AP exam. So we have relative extrema, which are also called local extrema. So relative and local are the same thing. Okay? A polynomial has a relative minimum or maximum where it switches between decreasing and increasing, or at an endpoint if it has a restricted domain. So the turning points, those are your extrema, because that's where we're switching from increasing to decreasing and vice versa. This extra part here where it says, or at an endpoint if the polynomial has a restricted domain. Okay, so one thing you may not remember officially about polynomials is that they are continuous. Okay, from negative infinity to infinity, it's just a continuous function. So if this was an arrow and not a point right here, then it would just keep on going, right? But they have restricted my domain because there's a point right there. We good with that? That's how we know for sure it's restricted, because otherwise it would just keep on going. All right, so my local minimums, okay, could be at an endpoint. This definitely looks like a minimum, right? At x equals -4. Then I'm going to go, I'm increasing, and then I change to decreasing, but that would be a relative maximum. Then I'm decreasing, and I'm changing to increasing. So then I have another minimum at 0, and then I'm increasing, and then I'm decreasing to infinity. Okay, you good with that? So then my local maximums, I started here, I switch here from increasing to decreasing at -2. Then we already said that that's a local minimum, and so then my local maximum is there at 3. Any questions about those? Okay, so your local or relative are any max and min that you can find, any kind of turning point that you have. Then we have absolute extrema or global. So I can have an absolute max or min or a global max or min, exact same thing, just two different words. So of all local maxima, so if you are going to be an absolute or a global, you have to first be a local, okay? And then you get to be a special local. And so the highest of all maxima or all local maxima is the absolute, and the lowest of all local min is, again, the absolute minimum. So this says here, the absolute maximum equals blank at x equals blank. So the absolute maximum value is the y value. Anytime you're asked for a value of the function, it's always the y value. Where it is, that is at the x value. So the absolute maximum value, what do you think it is? 2 at x equals 3. Okay? So this is the absolute value, the absolute maximum value. This is the place where it's at. Okay? Now, absolute minimum value, is that -3? No, because this keeps on going, right? And so that's going to go all the way down to where? Negative infinity. Is negative infinity a number? No, therefore it's not a value. Even if I wanted to use it as my value, could you tell me where it happens? No, you can't, because it's at infinity. So this answer here is just none. You don't always have one or the other. Okay? What questions you got? We good so far? All right, flip it over. All right, so now we're going to find and classify each type of extrema for the functions below, or write NA. We're actually going to write none instead is what I prefer, because that's what we've been doing. It's more consistent. All right, so relative minimum. What do you think about the relative minimum here? None, yeah? We don't have any, right? Because this, it doesn't only has one turning point, and then these go down to the infinities, so this would just be none. Good. Relative maximum, where? At 1. Make sure you're giving the x value and not the y value for the location. So what do you think about absolute minimum? None, because you have, remember, you have to be a relative before you can be an absolute, and we don't have any, so we can't possibly have any of these. And then absolute maximum value is what? 3 at x equals 1. So you can be a relative and an absolute, but not all relatives are absolute, right? Because you only have one of those. What questions you got? All right, I'm going to give you a couple minutes, and I want you to, at your tables, discuss B and C. And I am going to call on somebody to give me the answers when we're done. So you might want to actually talk to the people at your table and make sure we all agree and understand. Okay, let's see who's going to be my first helper here. Oh, Daniel Garcia, where are you, hon? Right there. All right. So tell me, on B, what do you have for your relative minimum or minimums? -2. Anything else? Nope. Y'all agree with that? Okay, great. Now can you give me relative maximum? 3. Is that it? That's it? Y'all agree with that? What are we missing? -4. Because it's an endpoint, and it can be the endpoint, not that it's not an arrow, okay? So -4 and 3. Okay, very good. Are we missing anything else? Nope. Okay. Thank you, Daniel. All right. Then Raquel. Where are you, hon? Okay. All right. So what do you think for an absolute minimum? Two at x equals 3. For your minimum? 2 at x equals 3. -3 at -2? Okay. What do y'all think of that? No? Okay, what? Can y'all tell me why it might not be right? Oh, we're just confused about what we were asking here. All right. So we have this relative, that's the only relative minimum we had, right? But this goes down to -infinity. So can I have an absolute minimum? No, I cannot. So then that, ooh, I just erased everything. Then my answer is none. Does that make sense? Yep. Okay. All right, so Raquel, with the help of your table there, absolute maximum, which is, I think, what you tried to tell me the first time. 2 at 3, yeah. 2 at 3. We agree with that? Yes? Thank you very much. All right, next helper, Emily. She's the one that's not here, right? All right, Dominic, where are you? That's you? All right, so tell me on C, relative minimum at x equals what? -3 and 3. Anything else? Nope. All right, we agree with that? Yes, okay. Relative maximum? 5, okay. And 0? Anything else? There's another one. What? And -4. Okay? Because this is a relative maximum, right? Because it's at an endpoint. Relative maximum, relative maximum. Okay? We good with that? Okay? Don't forget about those endpoints. All right, and then my last helper for today, Philip. Where are you, hon? Oh, same table. Let's see. Okay. Whoops. All right. Absolute minimum. What do you think? -3 at -3. If you get those mixed up, you get lucky on that one, right? All right. Absolute maximum. 4 at 5. Good. Y'all agree with that? Any questions on those? Okay, good. See, if you actually talk at your table and then you get something wrong, it's not all on you. You can blame your table, right? I'm just kidding. Well, in last period, somebody said something and it wasn't right. And then at the end, the guy at her table was like, look, that's what she had the first time. I convinced her it was wrong. It was my fault. It was so nice of him to step up and just throw himself under the bus for her. But all right, so let's look at some fun facts about polynomials. Between two real zeros of a polynomial, there must be at least one local, what's another word for local? Relative. Local minimum or local maximum So two real, and it says real zeros. Remember, two real zeros of a polynomial, there must be at least one local minimum or maximum, because once you go through to come back down, you've either got to go up and go back down or come down and go back up, right? So you're going to have a local, at least one local maximum or minimum. All right, and then we have polynomials of even degree. Okay, so polynomials of even degree follow the end behavior of what? A quadratic, a parabola, right? So that means if it's an even degree, the end behavior is either up, up, or down, down, right? Because of that, it must have either, so not both, but you have to have either. It's one or the other. You can't have both. A global, what's another word for global? Absolute. Global minimum. Or a global maximum. Okay, and then we're not finished writing, so don't put anything away here. We're going to do a couple of little examples right here. Global max min. Okay, so I want you to think about this. If I have a function and it's an even numbered polynomial and it has to either end up, up, or down, down. If it ends up, that means that down here there has to be an absolute minimum, right? And if it ends down, down, then there has to be an absolute maximum. That's what it's saying. So if I have g of x equals 4x cubed plus x squared minus 2. We'll just say that. Ooh, that said ma or min. That should say max. Am I guaranteed a global max or min for this function? No. This is an odd degreed polynomial, so it follows the end behavior of a cubic, right? So it's down, up, or up, down. So can it have one at all? No, because if one side of it is going up and the other side's going down, then I can't have an absolute max or a min, right? No matter what's going on in here, no matter what kind of other wiggles there are. So here, this is going to be no, and my reason is this is an odd degree polynomial. Whew. Okay. We good with that? So what if I have g of x equals 2x to the 5th minus 6x to the 6th plus 3. What's the degree on this polynomial? 6, because it's the biggest number, not because it's the first, right? It's an even numbered. So am I guaranteed to have one or the other? Yes. So now I have to know which one. Is this opening up or down? Down, so I have to have a maximum. So I can say, yes, I have a global max. And my reason is this is an even number, or even degree, I keep saying number, sorry, degree polynomial. I can't stop there. Polynomial. That right there, ooh, there's an L there, guarantees I have either a max or a min, and then I can say with negative, and neg is fine, leading coefficient. If that was positive, then it would be a global minimum. Okay? That makes sense to you? What questions you got? We good? All right, so you can go ahead and tape that in. You have all the tools necessary to complete 1 through 17 on the assignment. Tomorrow we will finish with the rest of it.